Hello, welcome back. This is the lecture that would have taken place on Friday, October 21st, 2022. It's my fourth day of quarantine from COVID. I'm feeling much better. I'm on antivirals. Knock on wood, everything will be good. I'll be out of quarantine tomorrow. I'm filming this also on Friday, October 21st, and I should be back and ready to go Monday morning, bright and early. So hope to see you there. I will certainly let you know if something changes that. Announcements as we get going. There is a new expert TA assignment up. It is due next Thursday, and I'll be saying more about other things and making announcements this weekend if needed. So look for that. Without further ado, let's do the astronomy picture of the day. And here it is, today's astronomy picture of the day. And it is an image, photograph of the Andromeda galaxy taken from New Zealand over a mountain range on the South Island. And this is, I guess, the Andromeda galaxy is a northern hemisphere object, about as high in the sky as this object gets any time of the year from New Zealand. This is a image that was taken over 30 seconds, and they set the camera to follow the stars so that he could get lots of photons as that sky rotated even over 30 seconds. And this is why the foreground actually looks a little blurry, because the camera was moving a little bit. And so although the stars stay nice and sharp, the foreground objects get blurry because they've been moved a little bit because the stars are moving themselves. Now, this is Andromeda galaxy is a spectacular thing in the sky. You can see this not this well. This takes 30 seconds of exposure and a bigger aperture than your eyes have, but this is visible, at least the central fuzzy part, to the unaided eye, right? You can see, if you know where to look, a faint fuzzy patch in the sky that is the Andromeda galaxy. This is, in fact, the most distant thing that you can see without a telescope or any other light gathering instruments. This object is the largest galaxy in our local group of galaxies. It's a little bit bigger than the Milky Way galaxy, and we're actually on a collision course with the Andromeda galaxy, and we'll collide with it in another 4.5 billion years. It's exciting stuff going on. If you're more interested in that, that's the other class that we teach on stars and galaxies, where you can learn more about that. Anyway, the point is, this is the most distant object you can see without a telescope. It is 2 million light years away. So the light that we're getting from it now left the Andromeda galaxy over 2 million years ago. And there's enough of it still, it's bright enough that we're still able to detect it unaided with our bare eyes. So next time you're out at a dark site, take along a star chart with you, look for the Andromeda galaxy, and then impress your friends with how long ago it was that light that you're seeing right now actually left that object. Okay, that's fun. Let's now go to today's review question. Today's review question. How much brighter will the sun appear from Earth at 1 astronomical unit than it will from Jupiter at 5 astronomical units away? A 5 or 10 or 25 or 100. Again, we don't have any actual top hat going on here, but pause the video if you like, work it out, see if you can figure it out, and then we'll work it out together. Okay. So let's try to figure this out. We know that the brightness of an object at a given distance is given by its luminosity divided by 4 pi times the distance to that object squared. And so if you know how bright it is at one object, at one distance, you can figure out how far it is from a different distance. In fact, we should make a ratio, as we tend to do with these things. The brightness at object 1, let's say the Earth, is the distance of the Earth, and the brightness at Pluto or Jupiter rather, we did this example for Pluto in the last class, is same luminosity, because that's just the luminosity of the object that we're measuring, which in this case is the sun, divided by 4 pi times the distance to Jupiter squared, right? So we want to know the ratio of Earth brightness to Jupiter brightness. That's what I've asked you. How many times brighter is Earth than the sun, is the sun at Earth than it is at Jupiter? That's a ratio, BE over BJ. So we can luminosity divided by 4 pi dE squared divided by luminosity divided by 4 pi d Jupiter squared. And look what these ratios do for us. All of these constants that we don't really care about just go away. And we're left with, you have to be careful because it's 1 over dE squared on the top, and it's 1 over dJ squared on the bottom. And so you could make this 1 over dE squared times dJ squared, and that is equivalent to dJ over dE quantity squared. And that's the brightness ratio of Earth to Jupiter, is the distance ratio of Jupiter to Earth, quantity squared, since distance appears in the denominator of these particular equations, it has to be opposite. If you have a ratio of BE over Earth to Jupiter over here, you have to be the opposite on the other side. Okay, great. So we know that the distance to Jupiter is 5 astronomical units, and the distance to the Earth, by definition, is 1 astronomical unit. So that's brightness ratio. How many times brighter is it at the Earth than Jupiter? Is just 5 AU divided by 1 AU, quantity squared. Those AUs cancel out. This is a unitless number. And this is just 5 divided by 1 squared, which is 5 squared, which is 25. So as seen from the Earth, we know from last class that the brightness is about 1,300 watts per square meter. From Jupiter, it should be 25 times fainter than that because it's 5 times further away, and brightness goes 1 over the distance squared. If you increase the distance by a factor of 2, it's 4 times fainter. If you increase it by a factor of 3, it's 3 squared or 9 times fainter. If you increase it by a factor of 5, it's 5 squared or 25 times fainter. Okay, now where were we? We were talking about telescopes, and we had talked about the different kinds of telescopes, reflecting and refracting telescopes, and we had even gone over the most important powers of a telescope, specifically light gathering power and resolving power. And we had talked a little bit about how light gathering power works. It's also a square law, although it's directly proportional to the square of the diameter of a telescope as light gathering power. And now let's talk briefly about angular resolution. What do I mean by angular resolution? Angular resolution is sort of defined to be how close 2 objects can be together and still have them be resolved as 2 separate objects. So let me give you an example. Here is 2 images of the same field, right? The same set of stars on the right as on the left. But the resolving power of the image on the right is vastly superior to the angular resolution of the image on the left. And you can see how this works, right? Here we have a very bright star here. I mean, you can tell where the bright stars are on this side, right? There's one there, there, and there, and there. And you've got some other bright stars going on here. But if you had to count the number of unique objects in this frame, you probably would get a couple dozen, right? Whereas once you increase the resolving power by quite a bit, you realize that there's probably hundreds of objects in this region. And so you can see, for instance, these 2 objects are clearly resolved in this image. You can tell that they're 2 separate objects. Whereas over here, they are not resolved at all. It looks like a single object. In fact, there's a lot of objects that are incorporated into the brightness of this particular object. So if you were trying to, for instance, measure the brightnesses of these objects and try to draw some inferences about what these objects were like, you would draw some incorrect conclusions, right? Because one, this is 2 stars and not 1 star. And really all of these stars have a lot of much fainter stars incorporated into the light that you're going to be measuring, and you just can't see it. In fact, you can even see that these are 2 separate objects up here, which are just barely resolved. You can just barely see that these are 2, in fact, separate objects. And so this is really important, right? The detail that you get on an image is set by the resolving power. And so clearly, the better this is, the better you're going to do. And it happens to be true that the bigger the telescope, the bigger the aperture you have, the better the theoretical resolution. It turns out that there's a resolution limit. You can do no better than a certain resolution depending on your telescope size. And the bigger you make your telescope, bigger the aperture, the primary light gathering element of your telescope, the better that limit of how good the resolution can be. So there's 2 reasons to make your telescopes big. One is you gather more light, and the other is you can theoretically do better at resolution. Now, I say theoretical. What do I mean by theoretical? Well, there are other things that affect the resolution of your telescope. And some of it's the optics, right? If you build it to slightly the wrong shape, or there's some waves in there, that's all going to affect the actual resolution of your telescope. But let's put all that aside. Assuming you've got great optics, the single most annoying thing for astronomers, especially when you're observing from the ground, is that the atmosphere gets in the way. And the atmosphere actually usually, for most professional telescopes these days, is far greater constraint than the size of the telescope at this point. So let's talk briefly about that. In fact, that brings us into the next part of this whole story, which is if you were building a telescope, let's say somebody gave you $10 million or $100 million to build a fantastic professional telescope, where would you put that telescope? Would you put it in Geneseo? Would you put it at the South Pole or at the North Pole or at the equator? Would you put it on a beach? Where would you put this telescope? We would have had, if this was a regular class, I would have asked for some input. I obviously can't do that here, but I do want you to think about it a little bit. Where would you put your telescope? One answer is you want it to be away from city lights. And this is, I don't get many soapbox moments in this class, but this is one of them. When you're out in the world and in places of power, think of the astronomers and be kind to us. Light pollution is becoming a real problem. As you know, the brighter the lights are in an area, the brighter the sky is. In fact, all the lights that we have on the Earth will at some point leak up into the sky and make the sky brighter. And when the sky is brighter, it makes it more difficult to observe very faint things in the sky. And here is a recent map of what the night sky looks like from various points on Earth, and you can see the entire United States is just awash in nighttime light. It's very difficult to truly get away from nighttime lights in this part of the world. And then there's lots that we can do to make this better, right? There are, excuse me, there are simple things we can do, right? Design your nighttime. Obviously, you need lights at night. I'm not saying you don't need lights at night, but there's ways that you can design them that make it more sky friendly. For instance, shield your lights, your nighttime lights on the street lights, and they're being designed in this way now, but they weren't always, to point down. Pointing down is where you need the light. And if you shield them and you direct that light down, one, you need less energy because you need less light. The more that leaks out into the sky is not where you need it. If you direct that light downward, you can save yourself energy and save the nighttime sky. And there are other tricks that you can do as well. But this is an important problem. and it's only getting worse over time. So where would you put your telescope? One is away from large cities, right? That's number one. What's number two? You want it on top of a mountain, ideally. You want it in a calm, high, dark, dry place. Why? Well, why would Geneseo be a terrible place to put your $100 million telescope? Lots of reasons. One of which is the weather here is terrible, right? We have cloudy skies most of the time, so you're going to be wasting, at least half of your days where the telescope isn't even going to be usable because it's cloudy out. You want it in a very dry place. This is the summit of Mauna Kea in Hawaii, which is one of the best locations for observing in the world. It's very rarely cloudy up here. In fact, you can see even when it is cloudy. In fact, this is the two summits of the Big Island of Hawaii. This is Mauna Kea in the foreground, and this is Mauna Loa, which is still an active volcano in the background. And you can see this is at 15,000 feet, right? This is a very tall mountain. And you can see in the background, there are clouds around, but they're below the level of the summit of Mauna Kea. And so even if there are clouds at the base of the mountain, often it's perfectly clear at the top because you're physically above those clouds. So that's what you want it dark, you want it dry. Those are important things. You want it to be high. And this is where the atmosphere becomes, this is where you can get over the atmospheric effects on your objects. The air hurts astronomical observations. How does that work? Well, this is the reason why actually stars twinkle, right? Stars twinkle. If you go into space, stars don't twinkle. Stars only twinkle because of the effects of the atmosphere. It's kind of like, if you can imagine, swimming to the bottom of a swimming pool and staring up at the universe, right? It's not quite that bad, but it's almost that bad. What happens when you're at the bottom of a swimming pool, and why does things up above the water look distorted? It's because there's waves on top of the water, and those waves, as the light interacts with those waves in the same way that a lens can redirect the patterns of lights as it passes through, the water can do the same thing as it's entering the water and going through different parts of the water. And so if you look at it, it kind of looks like a blurry, shimmery mess. Why? Because there's waves on top of that water, and that's changing the way that light refracts as it comes down. And the air, to a lesser extent, does exactly the same thing. And so instead of seeing a nice steady pattern, you're seeing these waves and the light changing and moving around a little bit as it comes through the atmosphere and eventually hits your eye. And this is why stars appear to twinkle, right? If you look at a single fixed source of light and you track it very quickly over time, you'll notice it's doing a little dance. And that's because the light from that object is getting bounced around as it comes in, and the actual location of that area of light actually moves around a little bit over time. And that is what the twinkling is. And if you put a detector down and you might get the theoretical resolution of your telescope is how big that dancing dot is. But if that dancing dot is doing a lot of dancing because of the atmosphere, you're going to get a very blurry image when you add it all up. And that's the problem with the atmosphere. The higher you build your telescope, the more of the atmosphere you're above. In fact, on Mauna Kea, you're over half of the way in terms of how much air there is to space. So that's extremely helpful, both for the amount of blurring that happens from these atmospheric effects, and also because we know that the atmosphere can absorb some of the wavelengths and photons as they come down. And so the higher you make your telescope, the less the atmosphere has to affect all of the observations that you're taking. So all modern telescopes are built on very dry mountain sites. And the two best in the world really are Mauna Kea in Hawaii and the Atacama Desert Plateau in Chile. one in the northern hemisphere and one in the southern hemisphere. So that's useful. Okay, you got some telescopes here. Actually, let's take a look at them. This is the Gemini telescope. It's an 8-meter telescope. This is the Subaru telescope. It's also an 8-meter telescope. These are the two Keck telescopes. We showed an image of those yesterday with the hexagonal segmented mirrors. These are both 10-meter telescopes, and there's two of them. And they're currently building a new telescope on this site that will be 30 meters in diameter. Guess what we call it? The 30-meter telescope. I told you we're not that good at naming things. All right. Anyway, so this is an example of what I was talking about. Here is why was the Hubble Space Telescope so powerful when it was launched in the early 90s? It was because it was the first real serious optical telescope that was fully in space, that didn't have to worry about any of these blurring effects at all. And here is, a star with a typical resolution that sort of the best you could do from the ground, and that same image as seen from the Hubble Space Telescope. It wasn't that the Hubble Space Telescope was bigger than all these other ground-based telescopes. It wasn't. It's smaller than the biggest by quite a bit. But it had the advantage of much better resolution because it was above the blurring effects of the atmosphere. Okay, now that was the story in the early 90s. We have come a ways since then, and adaptive optics has changed the way we think about how this can work. It turns out now that if we're clever, you can correct for the blurring effects of the atmosphere. How does this work? Well, here's an example of I think this is a VLT in Chile. Again, the very large telescope. And what they do is they shine a laser out into space at about the point where they're observing, like not right at where they're observing, but right next to it, right? So here's might be the image size, and then right next to it, they'll shine a laser that makes a little bright spot in the sky, and that laser light reflects back down, and it gets distorted as it moves through the atmosphere. If you can watch that motion, basically, of that fake star that you've made up there, you can correct for it if you have a fast enough system. In other words, if it moves like this, you can move your mirror in the opposite way to keep it moving in the opposite direction. If it moves like this, you can tilt your mirror in the opposite direction to move it back. And anywhere that this image seems to move, you can correct for it by tipping and tilting a mirror that will keep that object in place. And this is what adaptive optics is. And that's just the simplest thing you can do. It's much more complicated than that, of course, actually, because you can imagine each wave coming down having some shape, and that shape can be quite complicated. Well, not only can you tip and tilt this mirror, you can change the shape of this mirror more dynamically to correct for higher order terms in the distortions that are coming down from these stars. And the bottom line is you can, to very good order, take out the effects of the atmosphere if you have one of these systems installed in your telescope. And at this point, all 8-meter class telescopes and above have a system like this, because it takes your 8-meter telescope and makes it basically a space telescope in terms of the resolution that it can have. So here are some examples of Uranus from the same telescope without adaptive optics and with adaptive optics. And you can see this is the blurring effects of the atmosphere. The only reason why this looks blurry is because of the atmosphere. This now you're approaching the theoretical resolution limit of the telescope that you're using. And you can see amazing details in this, from small rings to clouds in the atmosphere to multiple breaks in the rings of Uranus that just aren't visible and possible to be seen without adaptive optics on. Same thing with Neptune. Here's an image of Neptune. You've got obviously way more detail on the adaptive optics enabled image than you had with the other one. So the point is, you don't need to go to space anymore to realize the optimal resolution limit of your telescope. You can put in one of these adaptive optics devices and get there. So here is a quick overview of all major telescopes at this point, both ones that are in service and ones that are planned. And I just want to spend some time going over with you so you can sort of get an idea of the scales of the things that we're talking about. Right? So remember, we started our discussion of telescopes with refracting telescopes, and I mentioned the 40-inch Yerkes Observatory refractor in Wisconsin. That's 40 on this scale. That's 40 inches in diameter, right? It turns out there was another refracting telescope that was never actually pointed at the sky or used that was slightly bigger, but we still are going to use 40 inches as the biggest sort of usable refractor in existence. And again, I also mentioned the Hale telescope. When it was built in 1948, it was the biggest telescope in the world, about 200 inches in diameter, about 5 meters in diameter. And you can see here is the Hubble Space Telescope, much smaller. It's only about 2.4 meters in diameter, much smaller than even the Hale telescope, right? This went into orbit in 1990. And here's the James Webb, much bigger than the Hubble Space Telescope, but much smaller than a lot of the telescopes that I'm going to be talking about that are in service on the surface of the Earth. It's way cheaper to build a telescope on the surface of the Earth than it is to send it into space. Here are the Keck telescopes. We talked about these yesterday in class. The GTC, the Gran Telescopio Canarias in the Canary Islands, similar to the Keck telescopes. There's lots of 8-meter telescopes out there at this point. Subaru, Gemini North, you saw in that image a little while ago. The Hobby-Eberly telescope is about a 12-meter telescope. The SALT telescope is on the 12-meter range. And these are sort of the biggest telescopes that are in use right now, right? The Large Binocular Telescope actually has 2 8-meter dishes, 8-meter telescope mirrors, and it can use them in tandem. You've seen pictures of the Very Large Telescope. There are 4 of them, and they can be used together. This is actually an interesting thing. If you have 2 telescopes and you use them together cleverly enough with a technique called interferometry, you can mimic the angular resolution of a telescope that has a size given by the distance between those 2 telescopes. And so if you are very clever about how you use your Very Large Telescope array, then you can get even better angular resolution than you could with just one of them. Magellan telescopes, again, these are all sort of in the last 20 to 25 years. Gemini South, these are the biggest telescopes that are currently in service. Now, that's not to say that that will be the case forever, because we know that there are some very large telescopes that are in design and being built as we speak. One of them is a 30-meter telescope. This is a U.S. consortium that is being built on the summit of Mauna Kea in Hawaii. There was some controversy about this one because the native Hawaiians were upset about another telescope going on the sacred mountain of the Hawaiian peoples. I think that's all been resolved and it's being built now, but you should go look that up if you're interested in that story. The European Southern Observatory, ESO, has started building the extremely large telescope, which will be almost 40 meters in diameter, right? This is a 40-meter telescope from one side to the other. Again, it's kind of hard to, what is 40 meters? Well, here's a basketball court, right? A basketball court is less than 40 meters across. This is the entire mirror from one side to the other will be well over the size of a regulation basketball court from one end to the other, the long way. This is an extraordinarily large piece of machinery. And these 2 projects are scheduled to be completed in the next 5 to 6 years or so. Other telescopes on the list, the Giant Magellan Telescope. which is taking, we figured out pretty easily how to make these 8-meter mirrors. And so what they're going to do is just take 7 of those 8-meter mirrors and put them all together and get a equivalent of a 25 or so meter dish across. And this is planned again in the next 6 to 7 years or so. They had talked about a 100-meter telescope, and they were going to name it the Owl Telescope. But you can see we're running out of acronyms here. It's becoming a problem. When you call your 8-meter telescope a very large telescope, and then you start building 40-meter telescopes, you have to go to extremely large telescopes. And the Owl Telescope was the overwhelmingly large telescope, right? Where do you go from extremely large? You're running out of adjectives. So this is the telescope problem. Don't worry, we'll figure it out. But it's kind of funny to think about where we go next with these adjectives. Anyway, so these are the largest telescopes in the world, both currently operational and planned in the next decade or so. But it's not, it's a lie, actually. These aren't the biggest telescopes in the world. These are the biggest optical telescopes in the world, because it turns out it's way easier to make a radio telescope. Why is it easier to make a radio telescope? Well, all satellite dishes are radio telescopes at some level. It's much easier to deflect radio waves than it is to deflect visible light waves. Why? Because they're much longer. If you want to reflect a visible light photon, you need to have your mirror polished to much better than the wavelength of the light that you're observing. And the wavelength that you're observing in the visible part of the spectrum is in the hundreds of nanometers, right? So you better get your shape of your mirror to within several nanometers over a 40-meter diameter set of mirrors if you want to get a very good image of what you're looking at. In the radio, your wavelengths are measured in centimeters and even meters. So you can build, it doesn't have to be polished, it doesn't have to be silvered, you can make it out of mesh, as long as the inaccuracies in that, the bumps and wiggles in that are much smaller than the wavelength of light, you're fine. And so you can build it out of anything, basically. And you will redirect those radio waves quite well. And so up until a decade or so ago, the Arecibo Observatory was built literally into a mountain in Puerto Rico, was 305 meters in diameter, right? But it was just sort of a giant satellite dish that had been built into the side of a mountain. In the past decade, the Chinese have built the 500-meter aperture spherical radio telescope, or FAST, and you can see what it would be like on the same scale, right? This is a half a kilometer, again, built into sort of a mountainous area where the terrain was sort of doing this anyway, but, filling it with a giant radio dish that's a half a kilometer on a side. So that is the state of where we are with telescopes right now. All right, I'll come back and do one more video for this class addressing the question of why we put telescopes in space. All right, see you then.